The chain rule.
Oh, are we writing it down today?
So you guys, well, I mean, it's in the book. You can put your notes if you want, but I want you to tell me so we can, as a group, we can write it down out up here.
I have to get out my paper.
If I have a composition of functions like this, f of g of x, and I want to do a derivative using like prime notation, so, using primes for derivatives, how would I write the chain rule in terms of f's and g's and x's and all that good stuff? Remember, maybe before we do that, just kind of what was our approach to the chain rule? We differentiated, we had layers of a function, and how did we always differentiate those layers? Yeah, good, okay, outside in, I can feel in a minute, right? So, so what's gonna be the first part of the chain rule, the first link?
F prime.
Ah, good, okay, yeah, because we have f of pan, right? So it's gonna be f prime of hand times g prime of x. Yeah. That make sense? If we look inside, we have g of x. So that's one way to write the chain rule. Now that's just a two-layer chain rule. Obviously, we could have as many layers as, we could have f of g of h of j of right. We could have all kinds of stuff in there. But you see the pattern there. With 2 is sufficient to see the pattern. Okay, the other way we write that is, and this is the way. Well, I mean, actually, this is the way we probably. This is almost probably the more useful way in a sense, because we almost always see functions of functions as being, parenthetically based, or to be layers within layers. But if we want to think about this as rates, and I'm going to go back to that clock example yesterday, if u is some function of x and v is, I'll do this with multiple layers. Well, I won't do that now yet. If u is f of x, sounds like bad grammar, doesn't it? Then dy du, or dy dx, I'm sorry, equals what? And if, I didn't put that right there down very well. What am I trying to say here? Y equals, oh, I know what it is. Y equals f of, that's f of u, by the way, be careful with that, where u is just some, call it,
It's clever.
g of x there, okay?
F of u.
What, so I don't really want this up here.
Specifically said f of u.
So how do we differentiate this? If I'm trying to, if y is written in terms of some function u, and u is written in terms of some function x, what's my, how do I use the chain rule there? So y is linked to u, and u is linked to x. How do I write that using this quotient form of a derivative? I'm not asking this question very well, am I? Let me just tell you what I mean.
Yeah.
dy du.
Oh yeah, I wasn't getting that. Yeah.
Du dx.
Okay.
And if we had a whole string of things, let's say that y was linked to u and u was linked to v and v was linked to x. I mean, we could just string together a whole series of derivatives like that, couldn't we? I mean, we could do something like dy du times du dv times dv dx, right? You see what I'm saying? As long as algebraically they all do this, I can have as many rates as I want to. I could have a clock that goes, I could add, instead of just having seconds and minutes and hours, I could have days on a clock, and I could have weeks on a clock and months. I could have all kinds of slowly moving arms on a clock, and I could just link them all by these rates. Rates of change of one with respect to the next times, you get what I'm saying? Well, I mean, it's, I can see how a person would link that. Okay, so then what this does for us, and I think you guys are fine with the idea of how to do a chain rule problem. What you don't want to forget is that chain rule can sometimes be like what if I had something like this? What if I had, let's say we had y equals the quantity x squared sine x strike that. x squared times sine of 2x plus 1 over
Just feel free.
sine of
Oh
cosine
God.
of x squared. And I wanted you, and that was all Q.
Hey.
Okay, now, we don't have to do this problem, but I want you to discuss what's the order in which you would approach this problem. I just want you to see, because if you can map it out, that's the best, that's the hardest part, is to map it out. Actually doing the calculus, once you've decided what the path is, it's just following some rules. So remember, we have to peel this thing from the outermost layer. How would we do this problem? What do we do first? Okay, yeah, we got the first layer is gonna be the power, right? That makes sense. Now, once I peel away the power, what have I got?
Quotient.
I've got a quotient, exactly, and I follow the quotient rule. Now, in the process of doing the quotient rule, I'm gonna get some nasty stuff going on. I'm gonna get the top times the derivative of the bottom. Well, what's actually the bottom times derivative of the top first, right? So what derivative of the top? Let's take that one first. What's going on there? What is that? What is the top? So I'm looking just in the blue bubble here, at the outermost level. What rule do I follow there? No. Product. It's a product, isn't it? Because I've got an x squared times the sine function, right? So in differentiating the top of this thing, that's a product. I've got to use a product rule inside of that quotient rule, right? So now how do you do that? Well, you just make a big set of parentheses, and you work inside the parentheses, literally. If I was doing the quotient rule here, I'm not gonna do the whole thing, but I would have just said v, so I get sine cosine x squared times,
Oh God.
that's gonna be the derivative of the top. I'm giving myself lots of room because it's a product, right? So now I gotta kind of just step out of the quotient rule for a second, step into this, just focus on this product rule on the top, right?
Yeah.
But that's just a piece of the quotient rule. Everybody see that?
Yes.
Okay, so inside these brackets, when I'm doing the product rule, well, I've got an x squared, that's no big deal. I get x squared times the derivative of that. Well, what's that? Okay, but that's 2 layers, isn't it?
That was a chain rule.
So that's gonna be a chain rule,
Oh,
right?
God.
Except the good news is, you don't even really say chain rule very much after, it just kind of becomes natural. Pretty soon you just start thinking of this as, and it'll happen very soon for you guys.
How would you do
When you're taking the derivative of that, you just think, oh, derivative of sine 2x plus 1, you forget that it's even 2 layers, you just differentiate it. You know, it's new now because we just learned it, but it's just a derivative, right? It just requires the chain rule. Plus this one times the derivative of that one, so that's in there, right? Minus the top times the derivative of the bottom, well, that's also a chain rule problem, isn't it?
Yeah.
Right?
Oh, yeah.
You see what I'm saying? The point I make here is just that even with the small number of rules that we have, things can still get pretty complex, right? I mean, you can still have multi-layer problems where things get pretty complex, right? Okay, last issue, we'll get out of here. The derivative rules. I've waited to give these to you, but now I'm gonna, because really, it's pretty lame to write them this way. If we just write the derivative with respect to x of x to the n, that's so limiting. It only works for a base of x, right? And we know that equals n x to the n minus 1, but we don't want to write it that way. Instead, we want to write it as a chain rule problem, where we're not going to limit ourselves to some x to the n. We're going to call it some power of x to the n. What we're going to say instead is the derivative with respect to x of u to the n. And u is just always understood to be some function of x. Could be sine x, could be a polynomial, could be anything, just some function of x. What's that going to be? By the chain rule. It's just the derivative of hand to the n, right?
Yeah.
U just represents, u is just our function of x, that just means hand, right? So n u to the n minus 1 times the derivative of u, which is du dx, right? So it's times That's our new way of writing the power rule. That's the general form of the
I
power
like the
rule,
other one better.
okay? Because we don't wanna just limit ourselves to this just being an X. We wanna take into account that regardless of what it is, the power rule still applies. It could be some more complicated function of X. Do you get my point? No, not really? Okay, so what that means
Oh,
is,
I get it, yeah.
this-
I got it.
this rule only applies to things like y equals x to the seventh, for example. But this one applies to things like, y equals sine of x squared to the seventh. See what I'm saying?
Yes.
Because this is telling us, because this is really just equal to sine of x squared to the seventh.
Yeah.
And the power rule tells us that the derivative of hand to the seventh is 7 hand to the sixth.
Yeah.
Now, it also tells us we gotta keep going. It tells us whatever's inside, well, we have to take that derivative next. And so in this case, if we follow, this actually applies here too, but what's the derivative of x with respect to x? 1, right? So if I apply the chain rule here, I just get the derivative of hand to the seventh is 7 hand to the sixth, 7x to the sixth, times the derivative of x, it's just 1, right? So we're done.
Yeah.
But we don't need to do that, do we? It's never gonna change anything, we're always multiplying by 1. But here, well, now there's the very real possibility that we got a lot more road to travel.
Yeah.
Right? And so we re-express all these original derivative formulas or rules in terms of u's instead. It doesn't change them, the rules are the same, it's still the power rule. All this says is the derivative of hand to the n is n hand to the n minus 1 times. The only addition is we gotta keep going. If that's a function of x, we have to differentiate that. Okay?
Yeah.
Make sense?
Yes.
So then what does, following that trend, what is this one gonna become? Say we take like, derivative with respect to x of sine x, which is cosine x. We don't wanna write it that way anymore. We wanna write it in terms of u's. So how would we write that? Yeah, derivative with respect to x of sine u, I guess, right? Equals cosine u times u is but u isn't this, u could be x, but it's probably not. It's probably some function of x. So if I wanna take.
dx.
Yeah, du dx. And the easiest way to write that, just a u prime. Okay, so that's how it appears in your book. You're gonna see them like, I can't remember if they use u, I think they use dud, I can't remember if they use u prime or dx, but that doesn't matter. Right, it's gonna write these in terms of u's.
Makes
Okay.
sense. Yeah.
Yes, ma'am.
Okay, with the sine x to the squared to the seventh, okay, so you did like how many times would you like take the derivative?
Okay, so, right, now, once we're done with the power rule at that stage. Good question, I see what you're asking.
Yeah.
You're saying, okay, so that's why we need a rule like this. For dealing with a situation like this one right here, we've got some function of x to the seventh. All the power rule part is telling us is that the derivative of hand to the seventh is 7 hand to the sixth, right? Then we gotta differentiate what's inside, and we'll just kind of respond to whatever's in there. We gotta apply probably a different rule now. Now we're gonna have to apply the sine rule next,
Okay.
right? So now we'd actually use this rule, wouldn't we?
So,
Once we peeled away the outer layer, we've got sine hand. The derivative of sine hand is cosine hand times hand prime,
okay.
right? So once I peel away the sine, finally I'm into the last layer of the function in x squared.
Okay.
And so I'd have to multiply by the derivative of x squared, right, which is just 2x. So this one's actually got 3 links in the chain, doesn't it?
Yeah.
Right?
Okay.
All the rules are telling you about is, this is the first link. This could amount to more than one link. It might be one, right, but it might be many, like it was in this case. It's just telling you, you gotta keep going. You gotta differentiate whatever's inside the power next. Okay?
Thank you.
Make sense? And so when we write things like the product rule, then, if I have something like this, and we just get something like u v prime plus v u prime, of course what's implied about that is v prime might be something big, right? All this is saying is that u is part of the product and v is part of the product. They're each factors in the product. But it might be that u has multiple layers to it. And when you differentiate u, that might require the chain rule. It's possible, right? It certainly did in that horrible example, right?
That was filthy.
Does that make sense? In this case, when we differentiated this quotient of u over v, man, the u was horrible, right? The u is, there's a lot of stuff going on in the u and a lot of stuff going on in the v. So when I apply, well, this is a product rule one, but if I had written down the quotient rule, every time we see a u or a u prime or a v prime, it's a lot of stuff. Does that make sense?
Yes.
I feel like probably we're good to go. I think you have to just do a bunch of problems and you're gonna have questions, but yeah. So let's head down.